Okay. We'll start with questions that you have. Ranking priorities. So the first step to either E or Z is to use what are called the Cahn-Ingold-Prelog sequence rules. And we've talked about the first couple of them, but we didn't go all the way in depth. So the idea here is that now, well, let's deal with this in the context of a carbon-carbon double bond. That's just looking at priorities of 2. Then we'll go to a chiral center where we have to do 4. So if I have a molecule like this and a molecule like that, so I've got those two groups. The Cahn-Ingold-Prelog sequence rules tell me how to rank these number 1 and number 2. Okay. And so rule number 1 is that you look at the atom that's attached. In this case, attached to the double bond. In the case of a chiral center, that's attached to the chiral center. And the highest atomic number wins. So in this case, we've got a carbon and another carbon. If it was carbon versus oxygen would win. So that's the first thing we do, is look at those. In the case of a tie, we now look at the attached atoms and then use rule number 1 to make that judgment. Okay. Again, highest atomic number wins. So when I'm looking at the CH2Br, what do I have attached to this carbon? I've got 2 H's and a Br. Down here, what do I have? 2 H's and that's C. So then what I do is I look at the total number of atoms that are there. And if there is an atom that has the singular highest priority, it wins. So in this case, bromine wins the priority for this group, and that would be the number 1 priority group, and the CH2I would be the number 2 priority group. Okay. In E and Z, what I'm going to do is I'm going to do that for the other 2 carbons on the other side, and then my 2 priority groups will either be cis or trans. And that sets up Z, which is the together cis, or E, which is a cross, that's for Zusammen and Endtagen. Endtagen's a cross, Zusammen's together in German. And so it sets up an easy system that I can use to determine, a cis-trans system that I can use to determine E or Z. But the Cahn-Ingold-Prelog sequence rules are what we use to determine. So let me give you let me just make that change. So which of these two groups has the higher priority? The isopropyl group or the CH2CH2I? Okay, I hear one for CH2CH2I. Ty? I hear one for isopropyl. Well, let's go through the steps. So carbon versus carbon's a tie. What's attached to that carbon? 2 C's and an H. What's attached to this carbon? 2 H's and that carbon. Do we have enough to break the tie? Well, I've got C's and H's, but since both groups have C's, I'm now going to basically count up. So this hydrogen's going to cancel one of those hydrogens. This carbon's going to cancel one of those carbons. So I basically am down to carbon versus hydrogen. Who wins? Carbon. And so this one would have the higher priority. Now, the reason I gave you this and why, the reason I gave you this is because you have to go through these series of steps. Just because there's an I or a BR or a CL there, don't let that trick you into saying, well, that's automatically the high priority group. If that I or BR or CL is too far away, you may never get to that to make that judgment. So just because it's there doesn't mean it's the highest priority. Okay? You have to go through these steps. And it is a singular atom of higher priority. If I had a CCl3 group versus a CHI group, who would win? And your periodic table is, you've got Cl, then you've got F, Cl, Br, and I. That's your halogen ranking in the periodic table. So between these two, who wins? CCl? CHI? So again, going back, carbon versus carbon tie. What's attached to that carbon? 3 Cl's. What's attached to this carbon? An H and an I. I should have made it a CH2. So CH2I. Did that change anything? Probably not. So of these atoms, is there a singular atom that has the highest priority? Yes, it's I. So in this case, that is the higher priority group. I beats Cl. So it's about the singular atom. Okay. Which would bring us to me saying, you never, and then I usually stop, because if I say you never do this, then somebody's going to say, you told us that's what we do. And I said, no, I told you that's what's not to do. So you never do something. It's always the singular atom. And that's how Cahn-Ingold-Prelog came up with this. They decided the singular atom would always give you the same answer. Okay. So it doesn't matter how many of a particular element you have. It's the singular atom. If you have atoms in both, then they cancel and you keep going until you find a point of difference. If there's no point of difference, then the groups are tied. And in the case of EZ, it means you can't have EZ because two of the groups are the same. In the case of chiral centers, it means that two of the groups are the same. That's not a chiral carbon. There's no RS. Okay. Right. So you keep going till you find a point of difference. Now, how do you handle double bonds? So someone asked about these two problems from the book. These are 612. Okay. So let's look at number 1. Right? Take a minute because I can ask you for number 1, I'm going to ask you what the lowest priority group is, and I'm going to ask you what the highest priority group is for number 1, because we're going to rank those 4 groups from number 1 to number 4. Because this is just the first step to getting to RS. There's 3 steps, and if you screw up any of those 3 steps, it doesn't necessarily mean you'll get the wrong answer. Okay. All right, for number 1, what's the low priority group? Hydrogen. We all agree with that? Hydrogen is always the lowest priority group. You could say, well, what if you had a deuterium there? Deuterium in the textbook is a D. I don't know that we've gotten to Ds yet, but when you see a D, you'll go to the periodic table, there's no element D. D is equal to a hydrogen with a mass of 2. With isotopes, the heavier isotope always wins over its lower isotope. So hydrogen is the lowest priority group always. And what's number 1? Oh wait, maybe it's not that easy to determine number 1. Well, yes, it will be. But that OH was attached to a CH2. I guess I thought it was attached to an OH when I quickly looked at it, which is another mistake you can make. You want to make sure you take them one at a time. So now we got to determine number 1. It will be the multiple bond, but we have to figure out why. So carbon versus carbon versus carbon. They're all tied. What's attached to CH3? 3 H's. Now you can probably guess that 3 H's is going to lose to anything. So if you said, well, CH3 is going to be number 3, you'd be correct. But what's attached to this carbon? 2 H's and an O. What's attached to this carbon up here? 2 O's. Now, you might say, okay, 2 O's beats an H, 2 H's and an O, but here's the problem. The problem is that for this CO double bond, there's only two things attached to it. It's a singular atom, so can I fairly compare three attachments to two attachments? And the answer is no, I can't. So Cahn-Ingold-Prelog had to figure this out. They had to say, well, what happens in the case of multiple bonds? We can't compare two attachments to three attachments. That's not a fair comparison. So then they came up with the idea of what are called equivalent structures. And the thing that throws people about equivalent structures is this is just a game so that C double bond OOH group, this carbon can have three things attached to it. It has no physical or chemical reality. It's just a system to give this carbon three attached things. And so when we write equivalent structures, what we do is we basically give the multiple bonds, and I'm going to say the multiple bonded atoms, we're going to give the multiple bonded atoms an equal number, or actually a multiple number of single bonds. Okay. What does that mean? That means if you have a carbon-oxygen double bond, that carbon is going to get two CO single bonds. If you had a carbon-nitrogen triple bond, it would get three carbon-nitrogen single bonds. So the way we draw the equivalent structure is we draw out the structure with only single bonds. Okay, so that makes it clear that the carbon only has three things attached to it. Then I'm going to replace this carbon-oxygen double bond with two carbon-oxygen single bonds. Here is carbon-oxygen single bond number one. I need to add a second. So in terms of the carbon-oxygen double bond, the carbon-oxygen double bond now is two carbon-oxygen single bonds. But we don't stop there, because we have to look at it from the perspective of the oxygen. The oxygen is doubly bonded to the carbon, so the oxygen needs two CO single bonds, or two OC single bonds. Well, here's number one, there's number two. So the true equivalent structure of this carboxylic acid is that structure. Okay. And all its purpose is for me to go, oh, that carbon has now three O's attached to it. So now I can make a fair comparison.
Why would you not bond the carbon to the oxygen at the bottom?
I could, but that oxygen, I can only bond a carbon to one of the two oxygens. And technically what I do is, since this is my oxygen that I wrote when I did my single bonds, I'm going to attach the carbon to that one, because I'm looking at this OC single bond and or double bond, and saying OC single bond number one, OC single bond number two. Now, there is a question about what do these oxygens and carbons do if they're just hanging there. And basically what would happen is that we would add hydrogens to those if we needed to go that far in our judgment. So if that oxygen and that carbon came into play, we would assume that there's three hydrogens attached to the carbon and that there's a hydrogen attached to the oxygen. Okay. So this is the equivalent structure. So now that carbon has three O's. If I go back here, where was that? If I go back here, now that has 3 O's. And so now I can make my comparisons. Now I can say 3 O's versus 2 H's and an O. The carboxylic acid group is number 1, and the CH2OH is number 2. CH3 is number 3. Hydrogen's number 4.
This molecule, would it be R or S then?
Well, let's come back to that. Let's come back to whether it's R or S. Kaylin? Yes, we would have to move it around. We have to move it around to get R or S. Or switch. Or do group switching. I just want to make sure everybody's okay with this. Yeah, I don't believe you. What would be the equivalent structure of a carbon-carbon triple bond? Take a minute, draw it out. I'll help you with that, which really isn't a lot of help. Do we have one? Like that? Do we agree with that? No? What don't you like about that?
Each of the center carbons share the carbons above and below. You have 3 separate carbon-carbon bonds. So they should just be bonded like left to right, left to right, left to right, and up and down.
So how many carbons do you want to attach to this one?
I attached one above, one below.
Okay.
And then one to the right of each of the upper and lower.
Okay. So let's figure that out. Let's figure this out. So if I'm looking at the carbon-carbon triple bond. So this carbon needs 3 CC single bonds. Single bond number 1, single bond number 2, single bond number 3. Okay. Then the other carbon I'm looking at is this one. And so if I'm looking at that carbon, I now get that needs 3 single bonds as well. Single bond number 1, single bond number 2, single bond number 3. So what we do is it's these 2 carbons that get the other 2 carbons each. I can see where you're taking the carbons that you just added and adding carbons to those, but we actually have to add to the carbons that existed at the beginning. So this carbon gets 1, 2, 3 single bonds. This carbon gets 1, 2, 3 single bonds as well. So this first one, that is the correct structure. So we only add carbons to the pre-existing atoms, is what we do. And then this would become a CH3. All of these would become CH3s if I got that far. Okay. So we only add these extra atoms to the pre-existing atoms. We don't add atoms to the atoms we add as the equivalents. So yours is just a difference between you don't have those bonds, you have them like that. Yeah, and so we don't add any atoms to those two carbons. We only add to the carbons that existed. So that's why the bonds go where they should, here and here. Okay. All right. So that's how we handle multiple bonds. Okay. And so that system of drawing the structure out with only single bonds and then adding the extra atoms to form the multiple number of single bonds is we add those to the atoms that were there originally.
So for the carboxylic acid, why don't we put the second carbon on the oxygen right there?
We put the second, what do you want to do?
That carbon?
Yeah.
Why wouldn't we put it on the oxygen that's already attached to the carbon? Like the one that's to the right?
Because my perspective is, so my perspective with this one is when I did the CO double bond here, this was my first CO bond, and then that was my second CO bond. This already exists, and that's not in play. Then my second perspective is I'm looking at it from the oxygen, so this oxygen now needs 2 CO single bonds, so there's number 1, and there's number 2. And this was the oxygen that was added, and then this carbon was added. This oxygen is only in a single bond, nothing gets added to it. So I was looking at it from the perspective of this oxygen right there. So then the most important thing here is that there are 3 C's in a triple bond. That carbon is attached to 3 C's. Right. So you could draw equivalent structures for all the carbonyl groups, all of the double and a carbon double bond, a carbon triple bond, and it's that first atom that we normally need to use to break any ties. So I don't think I've done this in this class. Right? This is the first time I've done this. I did do it in the afternoon class because somebody asked. And if you ask, I will answer, even if it's way ahead. So then I'm obliged to say that. So this is just fake. This is just for trying to figure out Cahn-Ingold-Prelog sequence rules. It has nothing to do with the chemistry. It has nothing to do with the physical property. It's just a game. And so my story is when years ago students came in my office. I think it was even in the old building, which is now the parking lot over here. And they said, Dr. Weaver, who went here as an undergrad and taught here for 45 years before he retired, taught organic for a long time. They said, Dr. Weaver's talking about phantom carbons, and we don't know what he's talking about. And I said, phantom carbons, okay. So now I have to think like him. And I'm like, what are you talking about? And they said, well, we're talking about like R and S. And I said, okay, phantom carbons. These are the phantom carbons. So I'm like, those are the carbons you added on in your equivalent structures. They aren't real. So they are like phantom carbons. So that's all we use that for, is just for equivalent structures.
What are equivalent structures like supposed to tell you?
All they are used for is this. I've got this carbon with 2 H's and a C, and I've got this carbon up here with 2 O's. I can't compare 2 and 3, so now I do the equivalent structure. I can definitely compare 3 O's and 2 H's and an O. And the only reason that that's important is because the singular atom wins. So this one has an extra atom, right, over this one. One of those atoms might be the singular atom that gives me the priority. So what they said was, no, we can't compare 2 atoms and 3 atoms. We need to compare equal numbers of atoms if we're going to use this singular atom winning approach. And so 3 O's versus 2 H's and an O, clearly 3 O's wins. But there may be another situation where an equivalent structure might have that extra atom that wins. And so that's why we have to compare 3 to 3. We have no choice. And so that's why they came up with the equivalent structures.
If where we have number 2 right now, if it was just an OH and not the CH2 before it, would you be able to assign that priority before we go and break the tie?
So if we had the OH there, we had the CH3 here, we have the H there, C double bond O, OH. So if my goal here is to do R and S. My immediate goal is number 1, 2, 3, and 4. So number 4, carbon, well, I don't even get that far. Carbon versus oxygen. Who wins? Oxygen. So this would become the number 1 group. Now I'd be tie breaking a CH3 versus a C double bond O, OH. And I wouldn't really need to know about I wouldn't need to do the equivalent structures because I go, oh, CH3, always number 3. Oxygens makes this number 2. So I wouldn't necessarily need to do the equivalent structures per se, right? The equivalent structures do come into play. We'll go down this road. Against my better judgment. Just to show you why equivalent structures are important. So let's say I had a CH double bond CH2 versus isopropyl. Who wins? Well, I can't tell because the C double bond C needs to be put in its equivalent structure. So again, what I would do is, and I would even actually expand out, I would put the hydrogens in place so I know my equivalent structures. So in this case, what would I have? I would have the first carbon needs to have 2 CC single bonds. So first CC single bond, second CC single bond. The second carbon needs 2 CC single bonds as well. First CC single bond, second CC single bond. So these 2 carbons are the ones that I added in the equivalent structure. Okay. And they're going to be treated as if they were CH3s. If I need them, I need them.
Why do you treat them with CH3?
Because that's the rule. The rule is I'd have a similar problem, right? I'd be comparing a C versus a CH3. The rule is give them the lowest priority group possible, which are H's. So now I can use those to make my tie breaking if I need them, and I need them in this case. So looking at this, carbon versus carbon tie. What's attached to this carbon? That's over here. What's attached to that carbon? 2 H's and a C. What's attached to this carbon? Sorry. This is why you go slow. 2 C's and an H. Right? That's what's attached to that carbon. 2 C's and an H. What's attached to this carbon? Two C's and an H. So they are tied. So now we go on. We go to the next attached atoms. Okay. What's one of the attached atoms? A CH3. Over here, what's one of the attached atoms? A CH3. Tied. Let's look at the other group. CH3 versus that group. In other words, C versus C. What's attached to this C? 3 H's. What's attached to this C? 2 H's and the phantom C. The one next. I don't count this one because I'm working my way from that out. And it would be, so if I said, well, there's a C here, there's also a C down here as well. So we just keep working out. And actually, I really should have said, oh, what's attached up here? A C, C, tied, 3 H's tied. Let's go to the other group. And so the other group has 2 H's and a C versus this carbon having what? 3 H's. And so who wins? The C double bond. C wins. That's how tedious this can get. But this is why the equivalent structures come into play. Because without the equivalent structures, I wouldn't have a systematic way of evaluating isopropyl versus C double bond C. Julia?
How come for like the dot structure you're able to add hydrogens and because none of the molecules are like CH3 in the original structure?
Right. So these are the rules. The rules are the phantom carbons that we added can't just hang as carbons. Because if I have to use them to evaluate something, I can't have carbon with, I don't know what's attached to it, compared to a carbon with 3 hydrogens. So the rule is all the phantom atoms get enough hydrogens to make them whole. That's why we added the 3 hydrogens to these two. And when we did the oxygen on the the carboxylic acid, the second O got an H as well. Because that's the only way I can use those atoms to make comparisons. And there are times like this when I need to use those atoms. So that's the complete set of Cahn-Ingold-Prelog sequence rules. But you got to be patient. You got to go step by step by step. I've already shown you some of the mistakes that you could make. Like looking here and thinking the OH is attached to the carbon and forgetting about the CH2 group. All right. So is everybody okay with that? So in an easy system, you do 2 to the left carbon, the 2 on the right carbon, number 1 and number 2, number 1 and number 2, the 2 number 1s. If they are together, if they're cis, it's Z. If they're trans, it's E. Yes. So the equivalent structure, so yes, the equivalent structure of that C double bond O, I added to this carbon up here, I added 3 hydrogens, and to that oxygen down there, I added an H.
So why do you have an H to 1?
Well, because OH, to be a neutral oxygen, can only have 2 bonds, right? Because it's an oxygen has 2 lone pairs. So it depends on the atom. A nitrogen would get 2 H's for neutral. Carbon would get 3.
Well, why did you put an H on bottom?
Because that was the atom that I added. That's the phantom oxygen that I added for that. And then this was the phantom carbon that gets the 3 H's. We can't have a single atom there. So that's what the rule says. And over here, the 4 carbons that we added, they need to become CH3s. Okay. So there's some problems in today's folder on doing those, on ranking them number 1 to 4 just as groups, and also in the R and the S in determining R and S. But we got to get the number 1 through number 4 sequence rules down first before we do R and S. So with this problem, they're asking for R and S. Okay. So now let's take the next step. The next step would be, once I've determined my numbers, now I need to do R and S. So I'm going to rewrite the structure here. And so I usually kind of will rewrite these with just the numbers in place, because ultimately when you determine the numbers, it's now about manipulating numbers, not about manipulating groups. So in order for me to determine R and S are the 2-handed forms of that carbon. Any carbon that has 4 different groups attached to it has the ability to be in a left-handed form and in a right-handed form. That's what chiral means, literally translated as handedness. So we have 2 forms of that carbon, 2 ways to draw those 4 groups so that they are mirror images of each other and they are not superimposable. Okay. Like your hands. If there are 2 groups attached to it, it is not a chiral carbon. Because in that case, you could rotate the molecule and you can superimpose. Right? No thumb, I can superimpose. So, in this case, in order for me to tell you the exact 3-dimensional structure around that carbon, I have to first orient group number 4 away from me on a dashed wedge. Okay, and that will create basically what the old time steering wheel model. Okay, they don't make steering wheels like this anymore. Right? They don't make them with the three things, and they don't make them with the shaft that you can visibly see. But that's the steering wheel model. So my 4th priority group's got to be pointing away from me. Then whether my 1, 2, and 3 group go clockwise would be R, and if they go counterclockwise, it's S. But my first thing after determining 1, 2, 3, 4 is to put the 4th priority group away from me, which means put it on a wedge. So in this case, I have a couple of options to put number 4 on the wedge. I can grab number 1, and I can rotate 4 into 2, 2 into 3, and 3 into 4. So I'm going to grab my top molecule, and I'm going to rotate it. And if I do that, Number 1 never moved. 4 came over where 2 is. 2 came where 3 is. 3 went where 4 is. Now, if you watch the video on this, looking at this, grabbing number 1 is the equivalent of basically rotating in a Newman projection. So if I was looking up towards 1 from underneath, I would see this Newman projection. And so by grabbing number 1 and rotating, in essence, that's what I'm doing. So if I do that, now my 4th priority group is away from me, going from number 1 to number 2 to number 3 is clockwise, so that configuration would be R. So number 1 in this problem should be R. That should be the R configuration. And I can put anything into a tetrahedron. Okay? I can put anything. On Friday, we should probably do some cyclohexanes. We can talk about Fisher projections. My intent today was to make sure everybody was okay with Cahn-Ingold-Prelog sequence and then start looking at the ways to manipulate the molecule to get number 4 away from me. And so the first way would be to grab number 1 and rotate it. So we had 1, and then 4 was where? The other thing you could think about is you can grab any atom but 4 and 2. Because if you grab 2, that's where 4 needs to go. So you could grab 1 or you could grab 3. So for instance, I could grab 3, that's a hand. Grabbing 3, if you wondered what that was. So number 4 goes here, number 2 goes here, number 1 goes there. So again, I'm not changing the original orientation of the molecule. I'm just rotating. So 4 came over here, 2 went to the top, number 1 went there, 3 never moved. Now number 4 is pointing away from me, going from 1 to 2 to 3, better be clockwise, and it is. Okay. So if you can put things in a tetrahedron, you can grab you got 2 choices, but you got to move number 4 to the dashed wedge. Your other option is what's called group switching. Okay. Now, I didn't invent group switching. I don't know when I learned this. I don't think it was when I was an undergraduate, but it could have been. I don't remember much about organic in those days. That was a long time ago. Probably some trauma in there as well. So the group switching is a way to rotate if you don't want to deal with the spatial reasoning and the spatial seeing this. And it's not put in any of the regular textbooks because apparently it's heresy to teach students how to rotate and not use spatial thinking. So it's the only place that this group switching is documented is in Organic Chemistry for Dummies for Volume 1. There is a Volume 2. So that's why I put the chapter in there in your folder from that, because that's the only place the group switching is documented, other than me. So the group switching means, very simply, you can switch any 2 groups on your tetrahedron any even number of times, and you have not changed the chiral center from what it was to begin with. Remember, you can't, if I try and, well, I'm forbidden to use this structure to determine RNS. I need to put 4 away from me. So in group switching, if you switch 2 groups once, you're going to get, if you switched once and put 4 away from you, whatever answer you get was the opposite of what you started with. Now, some people may do that. They may go, I'll switch once, and then if I get R, I'm going to write down S. If your mind works that way, great. Well, I don't know if it's great, but I mean, thinking opposite like that, that's fine. But most people want to make 2 rotations so that whatever they get is what they started with. And so that's why we can switch any 2 groups any even number of times, and whatever we get then is what we started with. So I could say, I'm going to switch 4 and 2. That's 1 switch. I need to switch 2 more, add 2 more numbers. I could switch 4 and 2 and I'm back where I started, but I didn't change anything. Doesn't help me. But I could switch number 1 and number 2. So now going, I hope, from 1 to 2 to 3 is clockwise, and it is. So the group switching allows you to basically rotate without having to rotate. And since I don't let you use models because other exams don't let you use models like MCATs and other AT tests and final exams, you have to kind of see this or begin to see it. So this is a way to do this without having to rotate and without having to look at models. Okay. All right, so we will, on Friday, we'll do more of these. I'll put online the sort of the readings. We may end up doing all of the enantiomeric excess and stuff. I'll answer those questions. But we may end up doing that on Monday. I may just give you a lecture on that because I have some stuff, including some real data to talk about chirality. So if you want to hold off on that, I'll adjust the schedule so we do that on Monday. Okay? But if you have any questions, post them, email me.